Okay, this setup will help us to investigate the behavior of light as they pass through a thin converging lens. So I have a parallel beam of light here. When I place a thin converging lens here, the ray that is parallel to the principal axis, it will bend and cut the focal point. And the ray that cuts through the optical center, it will go straight through without bending.
Rule 1. A ray of light which is parallel to the principal axis after refraction passes through the focus on the other side of the lens. Rule 2. A ray of light passing through the optical center of the lens goes straight. It emerges without any deviation. Similar to the convex lens, draw a line representing the principal axis. Again, we need to mark the points optical center O and F1, 2F1 and F2 and 2F2. All these points are at the same distance from each other. In this diagram, the distance is 2 centimeters. Note that in a concave lens, usually the F1 and F2 are on the opposite side compared to a convex lens. So F1 and 2F1 are on the right side and F2 and 2F2 are on the left side. You might find different conventions in different textbooks. Rule 1. A ray of light which is parallel to the principal axis after refraction passes through the focus on the other side of the lens. Rule 2. A ray of light passing through the optical center of the lens goes straight. It emerges without any deviation. The ray which is parallel to the principal axis after refraction by the lens passes through the focus. So this is our first ray here. For the second ray, let's use rule 2. The ray which passes through the optical center goes straight through, undeviated. So what does the intersection of these two light rays represent? That's right, the image. It's the image of my head, the top of the object, because we considered the light rays from the top of the object. So where is the feet of my image? It's on the principal axis. So you don't need to draw the light rays for the bottom of the image. Simply extend the top of the image to the principal axis and we get the bottom of the image. So as you can see, we found the position of my image here. What are the properties of an image? There are 3 points to consider here. First, is the image real and inverted or is it virtual and upright? Second, is the image magnified, diminished, or is it the same size as the object? And third, what is the position of the image? So what are the properties of the image here for case 1? That's right, the image is real and inverted. It's diminished. And as you can see, the image is formed between F2 and 2F2. You'll find similar diagrams in your textbook. Of course, I won't be the object there. The object is usually shown with an up arrow, since the object is upright and marked as AB. The image is also shown with an arrow and it's represented as A', B'. As you can see, the arrow is inverted here because the image is an inverted image. Now let me walk closer to the lens. I'm going to stand at 2F1 for our case 2. Once again, we need to use 2 out of the 3 rules. For the first ray, let's use rule 1. The ray of light parallel to the principal axis after refraction passes through the focus of the lens. For the second ray, we can use rule 2. The ray passing through the optical center of the lens goes straight through, undeviated. What are the properties of the image here? Can you see the symmetric nature of the diagram? I'm standing at 2f1 and my image is formed at 2f2. The image height is the same as the object height. That's my height. And can you see that the image is real and inverted? It's a real image because it's formed by the intersection of the rays. If you try drawing the diagram for this case, you might find that the image is not exactly at 2f2. Now this can happen if your foci f1 and f2 and the points 2f1 and 2f2 are not exactly equidistant from each other, or the rays are not accurately drawn. So to avoid such errors, an important exam tip for this case 2 is to use the cheating trick, which is first draw the image and then you draw the rays. Since we know all the properties of the image, we can easily draw it here. It's a real and inverted image, and this image is going to be exactly at 2f2, and the image height is exactly equal to the object height. So once you've drawn the image, you can go ahead and draw the rays. Now I'm going to move closer to the lens. So we have our case 3 here, where the object is between f1 and 2f1. I would suggest you to pause the video here, draw the ray diagram and try to find the image yourself. Also write down the properties of the image formed. So what's the nature of the image you got? That's right. The correct answer is it's a real and inverted image that's magnified. Here's the ray diagram, and as you can see, the position of the image is beyond 2f2. Next, I'll move ahead and stand at the focus of the convex lens. Again, we need to apply 2 out of the 3 rules. This is an interesting case because as you can see, the refracted rays are parallel. The refracted rays never meet. So where is our image formed? The image is far away, formed at infinity. The image is real and inverted, and it's highly magnified. Now let's look at the final case, where I move really close to the lens. The object, that is me, is between the optical center and the focus of the lens. Let's use rule 1 and rule 2 to draw the light rays from the top of the object. As you can see, the refracted rays here are divergent. So we need to produce them backwards to obtain our image. Wow! Can you see? The image is magnified here. So what are the properties of the image? The image is virtual and erect, it's magnified, and it's formed behind the object. Do you know a use of convex lens for this case? That's right. It's used as a magnifying glass, like the one used by Detective Sherlock Holmes.